Hello and welcome back. Today we're getting into the equation V equals IR as well as P equals IV. Before that, I wanted to introduce you to some symbols that you're going to see on diagrams or shorthand for electrical circuits. A zigzag little line represents a resistor. I think it's because it's similar to a light bulb filament. Two parallel lines, one longer than the other, represents a battery, and the lines are perpendicular to the wires. The longer line is the higher voltage positive side, and then just a regular line represents an ideal wires, meaning there's no resistance, no energy or voltage drop. Okay. So back to the water analogy. So if we had a circuit with water, we might have a pump which moves the water around, a valve to shut the water on and off, okay, and maybe a skinny tube which provides some resistance to flow, showing what would be analogous to an electrical circuit. So this is how electrical circuits are typically drawn. So here we've got our battery, we've got our short and long line, a switch, which is, you can see how it can close and complete the circuit here, but this represents an open switch. Okay, and here's our resistor, the zigzag line. Okay, right now the valve is closed and the switch is open, which means no current can flow in either situation. If I open the valve or I close the switch, then we can get flow rate. Okay, so we can have water flow and we can have electrical current flow. And here we've got current flowing from the positive side of the battery, which means we're dealing with conventional current. Okay, which way would electrons flow? Electrons would flow from the negative side of the battery around. Okay, so here we've got an open circuit, we've got an open switch. There's no current flow. Once we close the switch and we have a continuous path from one end of the battery to the other, it is considered a closed circuit. Now, so conventionally, the high voltage side of the battery is the positive side of the battery, and so this is the high voltage side of the circuit, and then this is the low voltage side of the circuit, which is the negative side of the battery. Okay, so when we pump water through a skinny tube, we lose pressure. Okay, pressure drops from one end of the tube to the other. When we pump water through, or when we pump electricity through a resistor, we lose voltage, okay, and we lose energy, and energy decreases from one side to the other. So we lose energy from the positive side to the negative side. Okay. So this is the Big Daddy equation in electrical circuits, and it's a pretty simple one. V equals IR. V stands for voltage, I stands for current, okay, which is measured in amps, and R is resistance, which is measured in ohms. So voltage equals current times resistance. If we solve this for I, or current, what this tells me is that if I increase the number on top over here, if I increase the voltage, then this side will get bigger. In other words, more voltage means more current. Okay? It also means if I make this number bigger, I'm going to make this side of the equation smaller, and therefore this side of the equation smaller. So if I increase resistance, I decrease current, which we already knew. But and that's known as Ohm's law. But it reiterates that for us, so it makes sense. So here I'm just reiterating that voltage is what pushes electricity around a circuit. Okay, voltage drives current. Okay, so your hairdryer is intended to run on 110 volts, 120 volts, which is what we have in the States. You go to Europe and you plug it into a 220 volt outlet, what will happen? Okay, well, if you plug it into twice the voltage, okay, you double this side, that means you're going to have twice the current on this side. The resistance isn't going to increase. If you and you're going to have twice the current, and you're going to fry your hairdryer. Okay, so don't do that. You go to Europe, they've got voltage adapters and things like that. They also have different outlets, so you can't plug it directly in. Okay. Uh, let's say I've got a 10 ohm resistor connected to a 9-volt battery. What will happen to the current if you replace it with a 20 ohm? Well, if I increase the resistance, it's going to decrease the current. Okay, as a matter of fact, if I double the resistance, I'm going to have the current. Okay, because it is a linear relationship. A 9-volt battery is placed on your wet tongue. Everyone's done this before to see if a 9-volt battery is still good. And your tongue has a resistance of around 3 kilo ohms. How many amps run through your tongue? Okay, so this is a simple equation. You plug in 9 for voltage. Okay, you're solving for I, and we got to convert 3 kilo ohms into regular ohms. You can't plug it in as kilo ohms. So that's 3,000 ohms. You solve and you get 0.003 amps, which would also be known as 3 milliamps. Okay, an air conditioner is rated for 15 amps through a 120 volt circuit. Okay, what is its resistance? Okay, so amperage is our I, it's our current, it's our I. Okay, we plug that in for I. 120 volts, that's our V, so we plug that in for V. Okay, and what is the resistance? Okay, so solving, we get the resistance is equal to 8 ohms. Okay. Is this AC unit really a 15 amp device? Okay, or is it only a 15 amp device when connected to 120 volts? Okay, well, it's really only a 15 amp device when it's connected to 120 volts. If I connect it to more or less voltage, I'm going to get more or less current flowing through it. Okay. Why is this bird perched? Why is he safe when he's connected or when he's touching this high voltage power line? Okay, well, it's not necessarily the insulation. Okay, he would be safe, or she would be safe even if there was no insulation on the wire. Okay, and that's because it's not truly voltage per se that drives current. It's voltage difference. Okay, and that's really implied when you say voltage, because voltage is always measured relative to some other voltage. Okay, it's always voltage difference. So it's really, he's got high voltage on one side and high voltage on the other side. There's no reason that that the current's going to go through him, because the current's getting pushed in from both sides. Okay, so there's no direction for it to go. Okay. So if we make the analogy of water, let's say we've got 2 full tanks of water. Okay, and we've got high pressure on both sides of this conduit here. Okay. Because the tanks are full. We've got high pressure here, we've got high pressure here, but we're not going to get any flow. Okay, this represents the bird. Okay, we're not going to get any flow because there's high pressure on both sides. Which way is the current going to go? Okay. Now, if you remove water from one side of the tank, okay, meaning you have a low voltage side, a low pressure side on one side, then we're going to get a current that is going to flow. Okay. So if the bird were to connect 1 foot to a ground wire, which is as low voltage as you can get, a ground, remember from last unit, then you'd have crispy bird. Okay. So if you touch a 120 volt circuit, okay, your dry skin has a resistance of around 500,000 ohms. Okay, wet skin has a resistance of only about 3,000 ohms. So you're going to get a lot more current flowing through your body or flowing around your body if you're wet, okay, because you have a much lower resistance. Okay, in order for current to flow, a complete circuit, a round-trip circuit, must be connected from one end of the battery to the other. Okay, which will have current? Which is a closed circuit? Is the first one a closed circuit? No, this side of the battery doesn't have anything connected to it. Okay, is this a closed circuit? Yes, it is, and this is also known as a short circuit because there's no resistance between the positive and the negative side of the battery. Okay, will this flow? Okay, well, you kind of have to know that this is connected to the other side of the filament riser. So this would be a complete circuit. Okay, so both of those will have complete circuit. Which of these will light the light bulb? Okay, only this one will. This one, the electricity won't go through the light bulb filament. It'll just go around and around this wire, but this one will light the light bulb. Okay. The second equation I want you to be familiar with is useful, but not as important, quote unquote, as V equals IR or Ohm's law, is the equation for electrical power. Now remember, power from before means energy per unit time. Okay, if we were looking at a waterfall and we were looking at the power of it, what two factors would determine how much power is being delivered to the bottom of this waterfall? Okay, what two factors would be if you were at the bottom of this waterfall, the power which you're getting hit? Okay, well, two things. One would be the flow rate of the water over the waterfall. So more water would mean more power. Okay. The second would be the height of the waterfall. Okay. The higher the waterfall, the more energy per gallon of water that hits you would be being delivered. So that would be the two factors: the rate of flow rate, okay, and the height or gravitational potential energy of the water, as you might say. Okay. So if we switch to electricity, okay, the power which energy is being delivered to my light bulb here depends on two things. It depends on how quickly the trucks are rotating around in this loop, okay, aka the electrical current, and it would also depend on how many green barrels each truck has. Okay, the more green barrels each truck carries, the more energy, the faster energy would be being delivered, aka voltage drop, okay, or voltage. So those are the two factors that come into play with our power equation, which is P equals IV, okay, PIV. Power, which is joules per second, just as before, also known as a watt, okay, is equal to electrical current, okay, the flow rate of the waterfall, okay, which is coulombs per second, okay, or an amp, and voltage, which is joules per coulomb. So when I multiply a coulomb per second times a joule per coulomb, I get a joule per second, which is a watt. Nifty, nifty. Okay. What power is required to run an air conditioner which draws 15 amps on a 220 volt circuit? These are pretty much plug and chug. I'm just going to go through an example or so. So P is what we're looking for, power. Okay. I, which is our electrical current measured in amps. Remember, current is measured in amps or amperes. Okay. And V is our voltage, 220. And multiply that together and you get 3,300 watts. So pretty much just plug and chug, nothing too complicated. Now, we've got two equations we can substitute in and get alternate forms of the equation. For example, if I substitute in V here for V here, I get power equals I squared R, okay? And if I substitute in I, okay, and substitute out I get P equals V squared over R. Okay, now these are a little more thought-provoking. Okay, so in the equation power equals voltage squared divided by R, okay, why is the voltage squared? Okay, why is it not just a linear relationship? Okay, well, if I double the voltage, what's going to happen is I'm going to have double the current. Okay, so my trucks are going to start moving around my loop twice as fast. So that's one reason that it goes up. The other is each truck will have twice as many green barrels in it, meaning it'll have twice the voltage. Okay, so twice the energy content. So that's the second factor why it comes in. Okay, so anyway, that's the reason for that. So these are a couple problems. I'm not going to work these, but we'll figure out which equation we would use. What is the resistance of a 40-watt car headlight intended to run on 12 volts? Okay, so we've got 40, that's our power. Okay, 12 volts, so that must mean we're using this form of the equation, P equals V squared over R. Okay, how much current is drawn from a 120 watt toaster with a resistance of 65 ohms? Okay, so we're looking for current. Okay, we've got power. Okay, and we've got a resistance. So that means we're using P equals I squared R. So I jot these equations down. P equals I squared R and P equals V squared over R, just to have. You'll use them in your problem set and on the test, maybe once, but they're probably helpful to have. So using these equations a little bit more, a 40-watt light bulb and a 100-watt light bulb are each connected to a 120-volt outlet. Okay, the question is, which draws the most current? Which draws the most current? Well, if we look at P equals IV, and we see that we've got more power, the same voltage, what about current? So as I increase power, that would mean I need more electrical current. So that means that the 40 or the 100-watt light bulb is drawing more electrical current. Okay, which has the greater resistance? We could answer this a couple different ways. One, we know that the 100-watt light bulb has more current. Okay, therefore it must have lower resistance. Or we can look at this version of the equation, where we know that, that for a given voltage, for more power, I'm going to have a smaller resistance. Okay, so the smaller resistance is going to give me more power, or the more power is going to have the smaller resistance. So just a way of interpreting things with those equations. If you've ever seen one of these, this is a multimeter. And they're pretty useful devices if you're working on electrical equipment. That'll measure voltage, current, resistance, among other things, as long as you know how to use it right. Typically during the regular school year, I'd give you guys some of these and we'd experiment around and use these in a lab, but probably not going to happen at least this year if you're listening to this during a COVID year. Maybe if you're listening to this in a non-COVID year, you will be using these. So a voltmeter measures voltage. Okay, an ammeter measures current. These are combined together in what's called a multimeter, which can measure voltage, resistance, capacitance, frequency of alternating current, things like that. Just a couple of side notes about using a multimeter. Notice the red and black probe. That's what you use and apply to the circuit to actually test it, and then it reads out on the screen whatever it is you're looking for. If you've got the meter set to voltage, then the meter just acts like an outsider, and you can stick the probes anywhere on the circuit, and it'll tell you the voltage difference across the two probes that you're doing. You don't have to disconnect anything or do anything. You just drop your probes in, make contact with metal, and it'll tell you what the voltage drop is or voltage increase. If you're measuring current, okay, you've got to set this to current. Okay, and there's an amp, a milliamp, or a microamp setting on the dial. And you actually have to disconnect one of the wires, and the multimeter actually becomes a wire and completes the circuit. If you were to stick these probes in the outlet in your home when it's set to this mode, you would have a short circuit and you'd blow a fuse or somewhere. In the voltmeter setting, when the probes are set in these holes and the dial is set to voltage, it's safe. You could even stick it in an outlet. I don't recommend you do this if your parents happen to own one. Don't go playing around with it and sticking it in an outlet. But if you have it set up correctly, you theoretically can. If you have it set up incorrectly, it is a bad idea. You get a short circuit and you'll blow a fuse. If you're measuring resistance, okay, you turn the dial to the ohm setting. You actually need to remove the component that you're testing and drop the leads across that. So here I've got this 8 ohm resistor. I don't know why the meter is reading out in voltage. It should be reading out in ohms. But anyway, just a real basic couple things on how to use a multimeter. That's it for today. So enjoy the rest of your day.